All right, for today's lecture, we are going to wrap up conductivity. We'll talk about something we were talking about last time and kind of extend on that. And then we will start on phase equilibria and phase diagrams. And so that's what today's lecture is going to look like. All right, so let's start with extrinsic semiconductors. So this is something we talked about last time, and particularly what I want to focus on today is the temperature dependence of these extrinsic semiconductors. And so here we've got a plot of the log of conductivity that you can see here versus 1 over T. So it kind of looks like an Arrhenius plot. But what we see with this extrinsic semiconductor is 3 different regions: region 1, region 2, and region 3. So this would be a good point. This would be a good time to sort of stop the video, even though we haven't talked about a lot yet. And I want you to sort of brainstorm some ideas and see if you can come up with what phenomena do you think is responsible for each one of these regions. And when we come back, we'll talk about each one and how we sort of get the mechanism in each one of those. So pause the video and we'll come back for that. All right, so we're back, and I wanted to sort of go through each one of these and talk about what we expect for each one of these. So first of all, we see that the slopes are different, right? And so we want to talk about the specific slopes and what that means, but let me just sort of uncover that for you. And you can see Peyton there, he's covering it up. So for the first region, you see that this is going to be related to E sub D, and so this should look familiar from last lecture. And then the middle is flat, and we see that the number there is constant. And then we have another slope up here, which is E sub G, so the band gap. And so again, that should also look familiar for that region. But let's go and look at this in a little bit more detail. All right, so since this is 1 over T, region 1 is going to be the low temperature region. So we're going to start with that one, right? And so if we think back to those extrinsic semiconductors, whenever we doped something in, we had what was referred to as a donor level, right? And so that donor level was very close to the conduction band, but there was a difference in energy from that electron to the conduction band, and that energy difference was E sub D, so the donor energy level, right? So at really low temperatures, there's not enough thermal energy for those donor sites to be elevated or raised into the conduction band. And so at really low temperatures, there won't be these free electrons from these donors. So we have to have some amount of energy. And so that's going to be related to what that donor level, energy level is. And so in this low temperature region, that slope then is going to increase with increasing temperature, and it's going to do so with the slope related to the donor level over 2K. And so that also means that we can look at the conductivity, and that's going to be related to that same term up here. So that's the first region, low temperature, where those donor electrons have not been elevated to the conduction band. All right, so that brings us to the intermediate region, region 2. So in this point, we've promoted or elevated all of those donor electrons to the conduction band, right? They've all been ionized in region 1. And so we reach at a certain point where that levels off, right? So at that point, the number is fixed at the number of donor electrons. So N sub D is what they're calling that here. So the number of donor electrons. So this is going to be the term fixed by the doping. So how much I add into the material to create those defects. And so this is the sort of the most common one that we think of because this is the one, this is the region probably close to room temperature or where it's being operated, where all of the donor sites are ionized And so basically the level remains constant in this sort of intermediate temperature range because all of those have been elevated. And so that then is fixed by the number. So that's the second level. Lastly, now we're at the high temperature. So at a certain point, it's remained flat with temperature, or 1 over T. But at a certain point, we see that the conduction goes back up, and in this case, quite drastically, right? And so this last level has to do with the ionization of electrons and electron holes that cross the band gap, right? So we saw that in extrinsically doped materials, we have extrinsic, but we can still have intrinsic if we're at a high enough temperature. And so this is the region that we're talking about here. So if we give it enough thermal energy, which is where that sort of separates region 2 and region 3, then we're able to promote electrons to the conduction band by crossing the band gap and leaving behind electron holes in the valence band. And so that's sort of the intrinsic region of the curve. And so that's a third region that we see, and it's the intrinsic one that has nothing to do with the doping of something, which is basically what gave you 1 and 2. So those are kind of the three regions that can happen for an extrinsic semiconductor when we're looking at conductivity. All right, so we've looked some at temperature dependence. That's what we just looked at with extrinsic semiconductors. Now what I want to look at for this last part on conductivity is to look at another variable, pressure, right? We've looked at partial pressure, oxygen particularly, and its influence on the amount of charge carriers with Brouwer diagrams. But now what I want to do is extend that one step further and look at its effect on conductivity. And so here with this one, I want you to take a look at this plot. This is for zinc oxide at a particular temperature, 900 degrees. And what's found experimentally, so this is an experimental curve, is that if we look at the log PO2 versus log conductivity, we have a slope of negative 1/4. And so I want you to see if you can use that knowledge that we talked about in defect reactions and Brouwer diagrams and see if you can apply that to why the conductivity would act this way with this change in partial pressure. So take some time, look at this, and see if you can sort of develop and explain why it would have this dependence for this sort of non-stoichiometric type defect reaction with changing PO2. All right, so we're back now. Hopefully you've had a chance to take a look at that, and I'll sort of get to the results here. So again, this is an empirical plot. We know that the dependency is minus 1/4 with log PO2, and so basically we need to think of defect reactions that can occur going from low to high PO2 and see if we can find something that would match that dependence of conductivity. And so you can kind of do this with trial and error. There obviously is going to be some educated guesses here, but one thing that you'll see here is the equation that we get here, and this is from our textbook as well. So if you take a look at this, you'll see that here the equation on the left side, the null statement, so basically everything is in its proper place. And then we create O2 gas from the material. So it's, again, losing oxygen in this case. And so with that, we need to sort of figure out how to balance this, right? So we're losing oxygen. And so this is basically referring to going from high PO2 to the low PO2 side, right? We're losing oxygen. And so we see that conductivity goes up. And so if conductivity goes up, then we can look at that in terms of an electron. So we have an electron here. And to balance that, there's obviously going to be multiple ways to balance that. But in this case, we're balancing it with zinc interstitials. And so that balances out this case. Like I said, there could be other options here for how to balance this reaction. One thing you'll notice though is that with others, it won't produce the same slope as what we need here for this empirical result. So for example, if I had an oxygen vacancy, that would not balance in the same way as this, and therefore our slope would be different. And so this is basically the experimental results that kind of lead us to one particular expression. And so in this case, zinc interstitials happening, right? And so when we write out the mass action expression, we get PO2 to the 1/2 times the site fraction of zinc interstitials times the site fraction of electrons. And so that's going to equal a constant, right? And so from this electroneutrality statement, if we were to take it a step further, we would see that those two sites, electrons and interstitials, should be equal. And so then we can basically divide everything by 2. And so that's where we get this negative 1/4 if we are rearranged. So it's basically the conductivity then is going to be proportional to the number of electrons, because we're taking this 1/2 divided by 2, and then if we move it to the other side, we're going to have a negative. So that's where we get the negative 1/4. And so it may seem strange, but this is kind of again, this is what's actually happening in the system. And so we can look at our defect reactions to try to model what's actually happening with that reaction. All right, so another example of that is copper oxide, Cu2O. So in this case, we have a different dependence with the conductivity with log PO2. So in this case, the conductivity increases with increasing PO2, as we see here. And it's actually a 1/7 fraction. And so in this case, we're obviously going to have a different reaction. The stoichiometry is different in this crystal. But in this case, if we look at this reaction, we can see that we will go from the null side, where we have O2 in the atmosphere. In this case, that O2 goes into the lattice sites for oxygen, and it creates vacancies and holes. And so that's how, when we increase the amount of oxygen, we can increase the conductivity in this case. And so same thing if we create that mass action expression here that we have, and then the neutrality condition where the holes are going to be equal to the vacancies, then we can simplify that, and in this case we would get a 1/8 dependency. So that would be our slope. And so you'll see that we have a 1/8 here and a 1/7. That's probably as close as we can do. So that's pretty close. There could be other factors happening, but again, it is experimental results. So we are close to that level. So this is just to get you thinking about some temperature and also pressure dependencies of conductivity that we could see in various materials.